1949 maximum absolute sum of any subarray, and I will be going through the intuition and solution. So if you want to pause the video and read it, you can, and now I'll go ahead and read it myself. So you are given an integer array nums, and the absolute sum of a subarray is all the numbers in the subarray added up and taking the absolute value of that after they're added up. So you're not distributing the absolute value, you do it after. And you want to return the maximum absolute sum of any possibly empty subarray of nums. And the absolute value is defined the same as in math, where a negative number becomes positive and a positive number stays positive and 0 equals 0. So looking at this example, we get 5, where the two numbers 2 and 3, when added up, give the value 5, and this is a subarray. And looking at other subarrays, you can see that, if we add -4 into the mix, this becomes 1, so this won't work. And same thing here, this would become 2. So just looking at all the subarrays, it's clear that this is the best one. And same thing for this example. And to understand this fully, and I will go through the brute force solution very quickly, which simply is, if we take every single subarray, starting with 2 pointers, then we could easily get the maximum value. So say we start with I equals 1, then we go to -3, compute that value, 2, compute that value, 3, compute that value, -4, compute that value, and then just do the same thing with over here, and over here. And in code, this would look like this. Super simple. We have our max value denoted here as maxi, and we go through for I and all nums, and we have our current, which is 0, and we will simply add the number and compute the maximum, where we take the absolute value of the current. Extremely simple solution, and it works. This should be pretty easy to come to the conclusion to, as it's just basic for loops. But if we submit this, obviously the solution is not this simple, because this is an O of n squared solution, and so the time complexity is simply too long, and we get a time limit exceeded. So we need to come up with another approach, and this approach has to come to us in below O of n squared. And the intuition in finding this solution is seeing that, hey, in example 2, we have that these numbers are essentially, the answer is going to be as many negative values as possible and as little positive values as possible to get the most negative number, or in this case, it's going to be the most positive numbers possible and as little negative numbers as possible. And when you think about it like that, you can realize that you can simply find some algorithm that gets the maximum of positive numbers, which is simply just maximum subarray. And so that will lead you to something that should just be memorized, which is Kadane's algorithm. And this is how it works. It's a really good explanation. You have a local max and a global max. And if we just jump straight into this example, you can see this all makes sense. And global max is simply just what is the maximum of either global or local, and it initializes at 0. And our local max is simply just our local max plus what we're currently at, and then just what we're currently at. So we can either, once we're here, we don't want this -2. It makes the value even lower. So we will get rid of that. And that algorithm is pretty apparent through here. And this is truly just something that you memorize. It's O of n time, O of 1 space, and thank you to this guy for that visualization. So that's something that you should just kind of know, and it's not expected that you come up with Kidane's algorithm during an interview. It's just truly something you should know, and even if you don't fully understand it, at least memorize it. But I will code it up here to help even more with understanding. So we have our defined Kidane's algorithm, and we'll use the same variable nums. And like it showed, we have a local max and a global max. And we only need to loop through once, so we simply just go for num in nums, and we set our local max to either the maximum of our current local max plus our current value nums, or just take the current value nums and take what's behind it. And our global max is really easy, which is simply just that. And we return our global max. Now, this code is obviously not done. And if you can spot why, it is because when we run this algorithm, it doesn't work for this second case. And that's because this is a negative case. And so we will simply just flip our nums. So we will get a new variable called nums flipped. And this is going to be I will code it out actually, because some interviewers might want to see, if they're not very fluent with Python, they might be confused on what you're doing. But for num and nums, we have our flipped nums equals this, and we'll set it to 0 times length nums flipped nums we'll do for I in range length nums flipped nums I equals -1 times nums I, and then simply we just want to return the max of these two, our flipped nums, so that we handle the negative cases as well. And that is accepted, and it works, and it's pretty efficient.